All right, here we go again. We're going to continue with enthalpy. And now, specifically, we're going to do a quick recap on enthalpy so that we are on the same road. And then we're going to start calculating specific numbers of delta enthalpy. And I'll give you some examples of how to do these calculations. So a quick, oh, there we go. We already see some spoilers over there. A quick recap of it is that we need to know that if we see a negative delta H, so we see a decrease in our bond energies in our reaction, that means we are exothermic. And if we see a positive delta H, this means we are endothermic. Yeah? And endo absorbs heat, exo releases heat. Yeah? And then if we have a graph over here, it could be asked, hey, is this endo or exothermic? Then you can say, hey, well, okay, I'm starting with a high amount of energy, ending with a low amount of chemical energy. So this delta enthalpy is negative. Yeah? And this is also then heat released, because we assume a closed system. Okay? Cool. So how do we calculate delta enthalpy? Well, we have this beautiful, beautiful table over here that you've been probably seeing and crying about. And what we do with this is quite easy, but we need to get used to it. So let's first figure out how we can actually calculate delta enthalpy. And delta enthalpy can be calculated by the sum of the enthalpy of my reactants. And remember, reactants means before the arrow in a reaction, right? Reactants are over here. So the sum of the enthalpy of my reactants minus the sum of the enthalpy of my products. And remember, products are on the other side of that arrow. Reactants turning into products in a reaction. Okay, so how do I calculate delta enthalpy? I take the values of all of my products, and I take the values of all of my reactants, and then I do reactants minus products. Okay, so let's say, as a small example here, I have some wood, I add some oxygen to it, and I turn it into CO2 and water. Let's imagine, okay? And now just quickly, out of my head, which is completely wrong, I'm just going to say this wood has 1,000 joules of energy. My oxygen has 600 joules of energy. And then we go to my products, and I can say my CO2 has 300 joules, and my H2O also has 300 joules. Let's just say for the ease of it. If we now look at my formula, we can see that we need to get the sum of products and the sum of reactants, which simply means adding these together. Yeah, the sum simply means the addition of all of the parts. So the sum, oops, that's not the symbol. That's neither. The sum of the enthalpy of my reactants, R, is equal to 1,000 plus 600, so 1,600. Yeah? And the sum of the enthalpy of my products is 300 plus 300, so that is 600 joules. Okay, so I have my H reactants, which was 1,600, and I have my H products, which was 600. What can I do now? I subtract the two. So 1,600 minus 600, my delta enthalpy is going to be 1,000. Yeah? Are those values correct? Probably not. But okay, this is just an example, right? Cool. That is how you would calculate it. 1,000 joule per mole. Cool. But, of course, the questions you're going to receive are going to be a bit more serious than that, but this is just an example that I can give you so that you see what does sum of reactants actually mean and what does sum of products actually mean, and how can we then work with those. Did I do something wrong? I didn't. I'm just tripping myself up. Okay, so let's do some examples using this graph. Because in this graph, what do we actually see? We see different bonds, and we see different energies, joule per mole. So we know that this is enthalpy, and the length, but we don't really care about the length. That's not for us. So we see different types of bonds and the amount of energy that these bonds have. Cool. Okay, so let's, for example, take CH. Let's draw a CH bond. Now I know how much energy is in this bond right here. It's 413 joules per mole. Sorry, kilojoules is what they use here. Kilojoules per mole. Cool. Now I know that. That's all that this graph says. And let's say I have an HI bond. Okay, well, let's look. Okay, it's here. That's 295 joules per mole. Kilojoules per mole. Sorry. Yeah, so that's all this graph does. That if I give you SF, you're going to look in the graph, you're going to see, here it is. That this bond has 327 kilojoules per mole. Yeah, that is how we read this graph. Nice. I hope this doesn't... Okay, never mind. I'm not going to even try. That's how we use the numbers in this table. Now, what's going to happen is that you will get, for example, a reaction. So let's say, give me the delta enthalpy of the reaction. That will be your question. And let's say that reaction is H2 plus Br2 becomes 2HBr. Okay. The first step that we need to take is simply draw my bonds out. So I'm going to start drawing all of my parts, all of my reactants, and all of my products, right? These are my reactants, and these are my products. Okay, H2. How do I draw that? I need to put down two H's, okay, and one bond in between. And now everybody's happy. H only wants one bond, so both H's are completely happy. Br is the same. It just wants one bond. So Br2, we draw it just like this. Nothing special, nothing crazy. And then we have 2HBr, HBr. That's one of the molecules, right? And we have two of these, so we have another one. These are the drawings of my molecules. Pretty easy. Cool. Now I need to figure out how much enthalpy is in my reactants. What is the sum of enthalpy of my reactants? So then I simply have to look. Okay, that HH bond, how much energy is in that? Let's have a look. Here we go. 432 kilojoules. 432. Br. That's another one of my reactants. Let's see. Voila. 193. Plop, plop. Cool. Now let's look at the sum of enthalpy of my products. I have two HBr bonds. Okay, what's an HBr worth? Bear with me. HBr 363. So we have 363, but we have that twice, so times 2 or just add another one of those. This is the sum of my products. And now, if we remember the formula, we need to have those reactants and minus the sum of the products. So here we go. The sum of this is, I don't specifically know, but let's 432 plus 193. That is my sum of reactants enthalpies minus my products. And that is 363 plus 363, so that is 726. And this gives us our delta enthalpy, which is equal to minus 101 kilojoule per mole. Yippee! And now what can I say about my reaction? Is it endo or exothermic? It is exothermic. Because if we remember, a negative delta H means that it's exothermic. And here we calculated a negative delta H. Cool. Let's do another example. let's say, hey guys, I need you to calculate the delta H of H2 plus I2 becoming I. And then we have two of those in a balanced reaction, right? 2HI. Okay. Step one, what do? We draw. So we're going to draw these bonds out. H2, we draw like this. I2, we draw like this. Turns into 2HI and another HI. Cool. 2HI. So these are the drawings of my bonds. Now I want to find out for my reaction, for my formula, the sum of enthalpy of my reactants minus the sum of enthalpy of my products is equal to delta H. That is my formula. So I just need to find out what all of these are combined together and then subtract the two. So HH, here we go, 432. 432 plus an II bond. 149, that's a weak bond. Minus, so this arrow as well, you can kind of turn into a minus if that helps you. Minus 2 HI bonds. What is one HI bond? Here we go. 295. 295 times 2, right? Because we have two of these bonds. Okay, then if we put that in my calc, I'm going to calc it. That means that this is going to be equal to, of course, delta H. And my answer, I think, correct me if I'm wrong, is minus 9 kilojoules per mole. So is this endo or exothermic? This is exo because delta enthalpy is negative. Yoo-hoo! Okay, one more to seal the deal. Where do we do this? Let's do it here. So again, let's just completely do it this time. Let's give the formula. Here we go. Is the sum of my reactants, the enthalpy sum of my reactants, minus the enthalpy sum of my products. And again, remember, reactants are before and products come after the arrow. Okay, so that is the definition of those two. So let's say I give you the reaction H2O being turned into 2H2 and O2. So that means that I need another one H2O here. Again, step one is we simply draw out the molecules. So here, H2O, we have two H's, one O. There we go. O wants two bonds, H wants one bond. This is correct. And how many of these do I have? I have two of them. So 2 times this. And maybe what's more helpful is to completely draw that out so you can more easily count the bonds that we have. Okay? This is an ugly one, but that's all right. Being turned into, so remember this now is what? Our reactants, because they are before the arrow. Our reactants. Being turned into 2H2, we know that this is H2. How many do we have? We have 2 of these, so like this, plus O2, so connect them first. Are these guys happy? Nuh-uh, because oxygen, it's in group 16, so it wants a double bond here. It needs 2 bonds to be happy. Okay, and these together are our products. This is what it's being turned into. And now we do the same. We need to check, the total enthalpy of our reactants and the enthalpy of our products. So let's see, reactants we have. Let's count them up. 1 OH bond here, another OH bond, so that's 2, 3 OH bonds, 4 OH bonds. Yes? 4 OH bonds. What is 1 OH bond worth? We look at our beautiful table. If we can find it here, 4, 6, 7. So one of these bonds is 4, 6, 7. This one's also 467. This one also 467, 467. So our reactant enthalpy, the product, sorry, rewind the tapes. The enthalpy of our reactants is 467 times 4, because we have 4 of those bonds. Yeah? Then let's check our sum of the product's enthalpy. So how much enthalpy is in our product? We have 2 HH bonds. What is an HH bond again? 432. So this dude has 432. So does this one. 432. So we have 432 times 2, 864 within these H2, plus what do we have? We have O2 with a double bond. Don't forget, O2 with a double bond is 495. And we only have one of those. So 495. Yeah? Then our formula right here, delta enthalpy, how do we calculate it? We take that sum of reactants, this, and we minus it by the sum of our products, which is this. So let's do that. 467 times 4, remember, because we had 4 OH bonds, minus, so you can turn this arrow into a minus sign, beautiful, minus 864 plus 495 is equal to our delta enthalpy, right? This is our formula. So what does that answer give us? Our answer should look something like, and again, correct me if I'm wrong, 509 kilojoules per mole. So is this endo or exothermic? This one is endothermic because it has a positive delta H. Here we go. Positive delta H means endothermic. So what can we then say about our reaction? If we know the delta enthalpy is positive, that means that our reactants, these boys over here, have a higher enthalpy than our products have a higher enthalpy than our reactants. So these guys have a lower enthalpy than what they are being turned into. That is what this positive delta H means. So our products have a higher enthalpy. How much higher? Well, 509 kilojoules per mole higher. So quite a bit higher. That's why it's endothermic. Exothermic here, we have minus 101 for this reaction. So that means that the enthalpy of my reactants is higher than that of my products. How much higher? 101 kilojoules higher. Perfect. And where did that energy go? It is released as heat. Yeah? That are the calculation examples. Hopefully that is clear. Enjoy it. Beautiful.